Hello, my name is JJ Belosky, and today I'll be presenting Lab 4 on oscillations. This lab focuses on analyzing the motion and energies of a mass spring system and comparing experimental data with a computational model. The purpose of this lab is to analyze the motion of a mass spring system and to compare the experimental data with predictions made by a computational model. The key models and physics principles we applied include Hooke's law, Newton's second law of motion, energy conservation principles, and the effects of gravitational force. Specifically, we modeled the mass spring system in 2D motion and compared the behavior observed in the experiment with the model. As a preview of the results, we found that the computer model and experimental data closely matched in the y direction, though for the x position, the experimental data graph was shifted slightly down and to the left, which could indicate incorrect assumed information. The energy graph matched expectations, with the total energy remaining constant and no change in total energy. First, Hooke's law explains the restoring force exerted by the spring when displaced from equilibrium. Then we consider the force due to gravity and apply Newton's second law to update the velocity and position of the mass over time. Lastly, we use the principle of energy conservation to account for the kinetic energy, gravitational potential energy, and spring potential energy of the system. Please look at the slide for all relevant equations used. In the experimental part, we use tracker software to analyze the motion of a swinging spring, extracting the X and Y position data. Then using GlowScript with Python, we created a computational model to predict the object's motion and energy changes. The initial conditions for the model were derived directly from the experimental video and provided there too. As we can see, we have a spring constant, the gravitational constant, relaxed length of the spring, the springs or the object's mass, and the initial conditions, position and velocity, which were derived from the first two position measurements in tracker to get the velocity. Our computational model considered two main forces, the gravitational force and the spring force. Together, they allowed us to calculate the total force acting on the mass during oscillation. You can see here, we compute these forces and the net force in the loop, which occurs as the object is swinging and affects the object's velocity and position. The energy components in our computational model were gravitational potential energy, spring potential energy, and kinetic energy. These were updated also continuously in a loop, maintaining total energy conservation throughout the motion. We also have to initialize these values at the beginning before we enter the loop to give us our initial values. When comparing the experimental and computational models, we found that the Y position values matched very closely, with the local maximums and minimums of the experimental data slightly more extreme, but hardly. In the X position data, the local maximums were less extreme and occurred slightly earlier than the model predicted. This means that our experiment, in actuality, the oscillations of the object did not actually go as far in the positive X direction as we expected them to. And they returned back towards the negative X position much quicker than we expected them to. In terms of energy, the total change remained constant, which was expected according to the energy conservation principle. Both the kinetic and potential energy varied sinusoidally, with the kinetic energy oscillating as the position and velocity changed, and gravitational potential energy alternating with the spring potential energy, as these two values are basically the yin-yang of each other in this situation. Again, we can see that the total change in energy remained a constant zero, which does in fact satisfy the energy principle. There are a few potential sources of error in our experiment. Damping effects such as air resistance were not accounted for in the model, and they would have led to energy loss over time that we did not necessarily predict in the model. Additionally, estimating the initial velocity based on the first two positional data points may have introduced inaccuracies. Lastly, extracting accurate position data from the video was challenging due to its low resolution and the importance of accurate data collection. By analyzing the data, we determined three clear periods for both the X and Y directions. These periods showed slight differences between the experimental and computational data, which could be attributed to the sources of error mentioned earlier. The discrepancy between the observed and modeled X position especially backs up this explanation, as the periods for X position are likely underestimated here based on the tracker data. Thank you.